So this is chapter 10.3. This is the last one that we're going to go through in chapter 10. And what this section does is, this is the standard error, it's called. And it's the standard error of the estimate. And what they're talking about with the estimate is the line of best fit. So last section, we had a formula for coming up with the line of best fit. And all that line of best fit means is pretty much what it says. It's a line that's supposed to represent all of your data points the best. Okay? And we talked about how you find that, like what's considered the best. And what they did is the formula basically measures the distance from the point to the line, and it does that for all the points, and it says which line would give you the smallest distance, like the smallest combined distance for all of those points. If we moved it up a little, down a little, if we kind of tilted it, which one would total give us basically the smallest distance, okay? That's not a perfect description of it, but essentially that's what it does, okay? Now this standard error, what this tells us is how far off is that line. So if you use that line to estimate something, how far off might you be? The best way of putting it is that it's the standard deviation of the line. If you remember the standard deviation, tells us how spread out data is in a bell curve, in a normal distribution. The standard deviation tells us how spread out is the data. Okay, so the bigger the standard deviation, the more the data is away from the mean, right? The more spread out it is. Same here. The bigger that the number is, that the standard error is, the further on average is that the points are away from the line. Okay, so here's what I mean by that. So I'm going to show you that slide from last section again. So the line of best fit gets all these distances, and it does that for every combination of a line, and it finds out which one's the smallest, and that's how it knows where to draw the line. But now, once that line is drawn, the standard error tells us kind of on average, again, it's not a perfect explanation of it, but on average, how far away is each point? Okay, so if your standard error is 3, the average distance from this point to the line for all of these is about 3. Okay, so the bigger the standard deviation, the less perfect the line is for the data. If you had a very, very small standard deviation, a standard error, I'm sorry, the line would really fit, like all the points would be really close to the line. The only time you'd ever get a standard error of 0 would be if our correlation coefficient, R, if it was 1 or -1, meaning every point was in a perfect line, the line of best fit would fit it perfectly, and our standard error would be 0. Okay, so here's how you figure that out. This formula right here. Okay, this is there are 2 formulas in the book. We're going to use this one. I think it takes a little bit fewer calculations. So it is the square root of the summation of all your y squareds minus a times the summation of y a times the summation of your y's minus b times the summation of your x times y's. Where this a and b come from is your line of best fit. So when you figure out your line of best fit, it gives you a value for a and a value for b. And that's where this comes from. Keep in mind that a is your y-intercept and b is your slope, right? Because we're going to go back a few slides. Oops, I went too far. Okay, so right here, remembering that a is your y-intercept and b is your slope. Okay, when you figure it out, remember you would write the formula like this, a plus bx. So just keep that in mind. So we use this. So this is example 1013 in your book, and this is the chart. So all your y's, the summation of your y squared. So what you would have to take is all of your y's, square them. That's what this number is right here. These numbers right here. These are all these numbers squared. And then the summation of that. So you add them all up. That's what this is right here. Okay. You subtract a. I'll show you what a is in a bit. The summation of all your y's. So all they did is they added up all of these numbers, and you get that right there. Minus b, we'll show you what that is. They took all their x's times their y's. So 1 times 62, 2 times 78, and so on. And that's these. And then the summation of those. So you add them all up. That's that number right there. And here are the numbers. So this is the 42,186 right there. A was positive 55.57. Okay, keep in mind it's supposed to be minus a, so that means a was positive. If you would have an a value of negative, this would have turned into plus. Okay, the summation of your y's, that's 496 right there. Minus, again, b was a positive number. B was 8.13, so when we stick it in there, it's minus 8.13. The summation of our x's and x times y's was 1778. That's right there. And then the bottom is your degrees of freedom. So there are 1, 2, 3, 4, 5, 6 measurements. So 6 minus 2 is 4. You do all this, take the square root, and you get 6.48. So what that means is, basically, on average, we're about 6.48. This line, the line that these numbers created, the line of best fit, was, you could say, on average 6.4 away. Okay, if the standard deviation was bigger, that'd be even worse. Now again, what I want you to keep in mind is, what is a big standard deviation or standard error? What number is big? It all depends on your measurements. Okay, if these measurements were in the millions, 6.48 would be very, 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 very small. If all these numbers were between 10 and 20, this would be very big. Okay, meaning that the line of best fit isn't that good. So it all depends on what this is. Okay, so this one, not too bad. All right, and that's all you got for this video. That's your last video of this chapter. And write down any questions you have, and we will see you tomorrow.